So hello everybody again to our Gamma seminar. Today we have the pleasure to guest Tomasz Sobczak, who is going to talk about an introduction to PDE Lie systems. So Tomasz, thank you for accepting our invitation. The floor is yours.
Okay, so thank you for a kind introduction, and I thank you the organizers to giving me a chance to say something about, as title says, a PDE Lie system. So in general, this talk is going to be to try to present the general, because the ordinary differential equations as a Lie systems, as probably well know from all of the people attending there. But what we want to do, we want to generalize, is to describe something something similar to Lie system for the partial differential equations. So this talk is constructed that I will give some really basic notions that are very useful to describing the PDE Lie systems, meaning the time-dependent K vector fields, just for the clarity, and some additional tools. And then I will try to describe, I will also recall what the Lie systems are for the ordinary differential equations, just to give a nice definition of partial differential equations as a Lie systems. And then, because the PDE Lie systems weren't quite studied, we had some geometrical structures, meaning, for example, the K-contact geometry, which appeared lately, is very useful to do so. I will give some recalling about the K-contact geometry, some notions that will be used. And finally, I will give an example. Of course, there will be a lot of examples, and mainly this talk is to show how many examples are of the PDE Lie system for now, and how we can analyze them via, for example, K-contact geometry, K-contact framework, and how we can use to develop some important notions. So, as a start, I will just recall what is a time-dependent vector field for the clarity. So, as a time-dependent vector field, you can think as a map from the Cartesian product of R times some manifold M, which gives us now an element of tangent space of a manifold. And our requirement to such a map exists to be a proper time-dependent vector field is that if we introduce some projections, meaning the canonical one from the tangent space of manifold to itself, or to the manifold, and some natural projection from this Cartesian product to the second part, which is just the point of the manifold, we require this, so that the time-dependent vector field will be such that the composition of it and the projection is just a like precisely that the diagram shown there is commutative. So we can go to the tangent space of manifold and project it, and this is the same as we would just project the second part. And what from the practical point of view is useful is that such a time-dependent vector field can be equivalently thought as a family, just T-parametrized family of regular vector fields. So time-dependent vector field can be viewed as a family of regular vector fields, which have some additional parameter. In this case, is R. Okay, so we have the time-dependent vector fields. Now we have to go a little bit further because we want to deal with the partial differential equations. And to do so, we have to introduce the notion of K-vector fields. So a K-vector field on M. Now we are working not only on regular tangent space manifold, but the Whitney sum of it. So we can think it as a K copies of tangent space. And if we introduce projection in this name tau Km, which takes us from this Whitney sum to the base manifold, then we can say that the K vector field is just the section of such projections. And using once again the diagram to illustrate it better, we say that this diagram, meaning if we take the section X, which gives us the tangent space, and we project it on the alpha element, meaning we have K copies of the M, and we project on alpha 1 by the projection tau alpha, we will this should be the same as if we take this alpha component some vector field, regular vector field. So it is once again very useful to think about the k vector field as a family of regular k vector fields that fulfills this condition. Later we will see that there are some nuances between being a k vector fields and the family of k vector fields. This is not exactly the same, especially if we will talk about the integrability of the k vector field, which will be useful later. However, for now, from the practical point of view, it's useful to think of this, as I said. So now we're going to combine both of those things to describe the PDE Lie systems. So time-dependent k-vector field is, as we can think, now we are going from not r times m, but rk times m to the Whitney sum. And everything is rather the same, but for clarity, some additional elements are introduced. Like, for example, now we are projecting not from r times m, but rk times m. However, from practical point of view, I want to think about this time-dependent k-vector field as a family of k-vector fields that each one of them is time-dependent. So this what I said is exactly this relation given what I'm underlying for right now. And why we want to introduce this notion of time-dependent k-vector fields? I'm going from more geometrical point of view than I would say the differential equation one, because now if we have a time-dependent k-vector field, we can say that it's have an associated system to it, which will describe the integral sections of it. What are the integral sections? The integral sections are exactly the solutions to the given partial differential equations, meaning if we have an element of the manifold M, the partial differential equation with respect to t, now we have to differentiate that before t was like a one parameter, now this is the element of rk, or in general, it can be element of some other manifold. Will be underlying that, for example, throughout this work, there will be some changes between the time dependent, or for example, R2 dependent, or R3, or so on. Just to underline that we have multiple, that this is the multiple indexed element. And each one of these partial differential equations has to be associated with one of the elements of this family, which in this case is denoted that, but I believe this is the same, and I believe it's more like eatable, meaning that this is the alpha vector field, which is time dependent, and of course is evaluated at gamma.
Tomasz, yes, one question. Could you comment on how restrictive is this approach to describe this approach by means of t-dependent k-vector fields? How restrictive is to describe general partial differential equations or ordinary differential equations? I mean, if you have a general partial differential equations, can you describe them by means of t-dependent k-vector fields in general?
I mean, I think you refer to the integrability condition, which I wanted to say.
No, it's more general than that.
Okay.
Okay, I will tell you one thing. Okay, in these partial differential equations, the unknowns are gamma, yeah? And you can see that in these differential equations, the partial of the unknowns in terms of the independent variables are functions of the unknowns and the parameter t, okay? This is set normally that the partials of the first derivatives of the unknowns are in normal form. You can every partial to write as a function of the time independent and of the independent and the dependent variables of the partial differential equation. This is very rare in partial differential equations. Most partial differential equations are not of this form. And writing a partial differential equations in this manner, it's by itself difficult, okay? So if you have a general differential equation, for example, imagine that you have a wave equation. Yeah. In general, it's difficult to write it in this manner. Okay. Yeah, this is what I wanted to tell you. Okay, that's
okay. So thank you for the comment, but yeah, it's a good point. That is kind of rare, but for our advantage is that we managed to find some really interest, that the things when it works are the examples that are interesting for our theory. So this is, but yeah, this is thank you for the comment. So for now, now we have introduced the notion of time-dependent k-vector field. So as a kind of trivial example, but it will mainly serve to recall what the Lie systems are, is just the ordinary differential equation, which of course there will be the Riccati equation as an example, meaning if we have a first order ordinary differential in such a form known as the Riccati equations with functions b1, b3, b3 are some arbitrary time dependent, and t this is one belongs to R. Then this is the time dependent one vector field, or just the time dependent vector field on R of such a form. So in our case, this is maybe not interesting for the PDEs. However, it mainly serves as a recalling for Lie systems because, as we know, as I mentioned it many times on this seminar, the Riccati equation admits a superposition rule, meaning that if we want to get the general solution of this equation, we can express this as a function which is time independent. The solution is time dependent, but the function itself that uses the particular solutions and the constant is time independent. We can generate almost all solutions via this function. And this is the property that characterize Lie systems and are interesting from our point of view. So to give the connection, the bridge between admitting superposition rule and some geometrical structure is that if we have a first order ODE on M and it admits a superposition rule, meaning we can find the similar phi as previously, if and only if this time-dependent one vector field, or just the time-dependent vector field, can be decomposed in such a manner, meaning that we can express this as a sum of some time-dependent functions. T, once again, I will underline it because it will change later, is just element of R, are some arbitrary functions, and the vector fields that are here in these decompositions are spanning the finite dimensional R-dimensional real Lie algebra of vector fields. And this algebra has a special name. It's called the Hilbert algebra. And it doesn't give us much about the superposition itself. However, it guarantees that the superposition exists. It also doesn't say that the superposition is unique. Maybe this decomposition don't have to be unique, but if it exists, we are 100% sure that there is some superposition rule. And going back to the example, once again, by considering time-dependent vector field or time-dependent one vector field X, we can see that indeed we can decompose it in such a manner that the time-dependent part is B1 to B3, and the R-dependent part is generated by three vector fields X1, X2, and X3, which are indeed closed under taking the commutations, meaning they span, in this case, three-dimensional real Lie algebra. So the idea behind this is the recalling for the Lie systems, and the idea behind the generalization to this notion is exactly that if we have a time-dependent one vector field that can be decomposed in such a manner, we want now have the similar decomposition for the time-dependent k-vector fields for the PDEs. So the Lie-Scheffers theorem for PDEs that I want to present is that if we have a time-dependent system of PDEs that admits a superposition rule, which can be understood the similar way as in the ODEs, that we can express the general solutions via the particular ones, constants, is that our time-dependent k-vector field can be decomposed in such a manner, meaning once again, we are thinking about that we have a k-vector fields, and each one of them can be decomposed as in the previous theorem, meaning that each alpha, x1, x2, x alpha, can be decomposed using some time-dependent function, and which is, I believe, also important, the vector fields only depending on the manifold. However, there are the same vector fields for each x alpha. These coefficients can change regarding to the alpha, but this is the same family of vector fields. That's once again spans R-dimensional real Lie algebra. And additional thing, and this is the point that I was saying, we want to, if we want to have a PDE Lie system, our time-dependent k-vector field associated with the system has to be integrable, meaning that elements of this has to commute between themselves, so these commutators equal 0. And this is the different part. There is a subtle difference visible between k-vector fields and the k-vector field, meaning we know, for example, from Bäcklund's theorem, that integrable, if we have a k-vector field, so the distribution spanned by them is integrable if it's involutive, meaning this commutator could be expressed as the elements of this distribution. However, integrability of the k-vector field is a little bit stricter, meaning we require that this commutator vanishes. So it's 0 for every x1, x2. So this is, for example, the difference. But from the practical point of view, it can be viewed that every element of this family can be expressed as in the previous statement. So, as in first example of PDE Lie system, I will give the notions, and basically from now on this talk, given that I will give some context where this equation, what is important and where it appears, and it occurs that it can be described as a PDE Lie system. So, and everything that will happen there will be in literature, so I will give you the links where can you find it about a little bit more. But for now on, as a first example, we will consider a so-called G structure. Namely, the G structure is a differential one form, which we denote their epsilon on m-dimensional manifold M, that have their values are in the some Lie algebra G, and it fulfills such equations, meaning the differential of such a differential one form, what x1, x2, is just the minus commutator of the values at x1, x2, or written in such a manner for all vector fields x1, x2. And this is, the G structure is important because it's really connected, for example, with the Cartan geometry, principal bundles. And for example, the Mauren-Cartan form is indeed, can give a rise to a G structure. So there are some examples of this. And this description, which I will give you, is more in detail in one of the literature, but give you with a brief understand what are we want to do, what we want to find with this G structure, is to mostly want to find the first integral of the given differential epsilon. And we call such a first integral such a map that the tangent map of it, composition of such a tangent map with R, which in this case is denoting by taking the vector in the tangent space of a Lie group, which acts effectively on n-dimensional manifold, note, that takes the vector from the tangent space of G to our Lie algebra Gothic G, which can be understood by taking the vectors from some point to the identity of G. And if we make some these compositions, if it's exactly the epsilon, we call the F the first integral. And it occurs that to find the first integral, we can use the additional function, and this is this function F is important for us because it admits a superposition rule. In the literature, in the Dubov and I don't forget the next surname, but it will later, they say that this function, which helps us find the local first integral, admits a superposition rule, so it should be a PDE Lie system. So just to be clear, how to obtain this local integral, we have to fix point on the manifold N, and then by such equation, meaning the push forward of a map will be equal to the composition of our initial differential one form with additional homomorphisms. I mean, I don't want to go really into details because they are quite complex and are a little bit well defined in the literature, what I give you. However, finally, what we have is that our function f that generates the the first integral can be expressed as a sum of its elements of homomorphism and the differential one form, the value of the differential one form in Q. And indeed, if we locally express it as in there, we can see that the system admits a time-dependent, M-dependent, this is what I said because we have parameters coming from M-dependent M vector field x1 to xm of such a form. And to see that, because as we said, we found out that authors claim that the superposition of F exists, we have to check if this vector field, and there should be bold H, I'm sorry. And yeah, no, it's okay. No, it's okay. It's okay. So each one of them, okay, is okay. Meaning, if they claim the superposition rule exists, meaning this vector field should be integrable, meaning xy, every xy should commute with itself. And by some tedious calculations, as we can see, they are quite long and tedious. However, I believe this part is the nicest one because we can rewrite it as exactly the condition for epsilon to be a G structure. This has to be zero. For example, also if epsilon would be a Mauren-Cartan form, it's also zero. So it actually is fulfilled. So it has the superposition rule in our point of view. So it is a PDE Lie system. So I will give you also another example. This one, once again, this one is related to the Floquet theory. In our case, PDEs also are related to the theory of the periodic differential equations. I mean, the Floquet theory describes the differential equations in normal form that have, like, the values of the vector fields are periodic in parameter. And in general, it could be related to ODEs. However, we have two parameters, periodic one. We can think about the surface in, for example, the R-dimensional Lie group. And this example mainly is to show you how we can create the PDEs on the Lie groups and how they relate, because this is the very useful, they have the really useful properties that will be later visible. So in this case, if we want to describe the tangent vectors to the image of our Scheffers, we have two parameters, so the partial by S and partial by T could be expressed as a linear combination of just the push forwards of the basis of the Lie algebra, by push forwards of the right action at the point sigma S and T. And in both cases, as you can see, this coefficients depends on which one we are push forwarding. Yes, for example, this is the S, there's a T. However, this is the important notions. We are working on the basis of the Lie algebra, which is isomorphic to the tangent space of G at the neutral element. And why is that important? Because we have the right invariant vector fields there. We can introduce the base as the right invariant vector fields, and we can rewritten our system as similar. So now, instead of push forwarding by right action, we say that this is the value of the right invariant vector field at sigma st. And once again, in this case, it's purely visible that we have R2 dependent or as S2 as the dependent two vector field associated with such a differential equations. And if it's a PDE list, there's some additional conditions, I mean the integrability one. So if the integrability conditions is fulfilled, our system is a PDE system. So PDE system on Lie groups are really useful because of these notions that we always have this right invariant vector fields, and this also will be useful, for example, if we want to analyze them via the K-contact framework. So we really appreciate that we have this, and this example also is an introduction for the theorem that we want to give that relates PDE Lie system on Lie groups or with the PDE Lies not only on some regular manifolds.
Just one comment, Thomas. The Floquet theory you wrote before appear, for example, to work out geometric phases in certain systems.
Yeah.
So it has relevant applications in quantum mechanics approaches from differential geometry. Thank you.
Yeah, for sure. Like the application, I'm not expert on every. There are many examples from different fields, and I'm not expert on every them. But however, this is what I know is that the Floquet theory is relevant if some have a periodic orbits, or as you said, some geometrical structures. Like so, yeah.
Yeah. Sorry, may I have a question? Do you have any concrete example with a particular choice of a Lie group? I mean, I would like to see how the integrability condition is restrictive in this case.
Oh, I don't have an example. However, I see. I mean, this is the thing how we can for sure analyze. I mean, give some particular example and see how it's restrictive. I don't have particular example in mind for now.
Bartosz, I don't remember quite well because I wrote this, I don't know, 15 years ago. That maybe in the original work they have some calculations for particular cases, not exactly as done in here, but quite easily translated into this language. Because I think that it was for Riccati questions. For Riccati questions, it can be described with the Lie group SL2R. So I guess that this is the thing that it appeared. Okay, or I know other example, for example, with maybe with SU3 too, okay, with SU2 to study 13 oscillators. So a couple of examples with applications can be written, okay, and if they are not in the original works, they could be described quite easily. Thank
you. Okay, thank you.
So as I said, I mean, the main point of this example is given that being a PDE Lie system on the Lie group is very handy. And the theorem I want to give is like, how can we describe the PDE Lie system on some arbitrary manifold with the PDE Lie on a Lie group? Meaning, if we have a partial differential Lie system of partial differential equations on a Lie group of such a form, meaning once again we'll use the right invariance in this case, because if we have a Lie group, if we introduce the Lie group action on the manifold that we are interested, then the solution of PDE Lie system on M, which are exactly those when this X alpha, this value of this vector fields as just the push forward of the right invariant vector fields, can be expressed as just acting this Lie group. The solution to the second equation can be expressed as a Lie group action on our solution to the first equation, equation 4, and some additional starting parameter. Yeah. With gamma y0 be some starting point. So we can analyze the solutions on the manifolds by solving the solutions on the Lie groups, which are really, and we can like overuse the properties of the right invariant vector fields. So as application of this theorem, as one can see, that we can consider such a different, I mean, we are going from the other side, meaning the application will be somewhere there in the middle. For now, let's just consider exactly what I said, meaning the PDE Lie system on the Lie group of such a form. So we have that the element of G is a Lie group, that the partial differential with respect to some one parameter T is proportional to G, the same with the C, and the proportionality are just some functions that are taking the values in the matrix Lie algebra of a given matrix group G. And the integrability condition, which also we require to be a PDE Lie systems, can be written in such a manner. And the interesting part of this is that if we have a joint, if we take a G and introduce the group action by the adjoint Lie group action on G related to this, we occurs with such a differential equations, which are strictly the Lax pairs. And the Lax pairs are the notions of such a pairs to, for example, matrices, operators, and so on, and are, for example, interesting from the point of view that if a system has such a Lax pairs, if we can express a differential equation using the Lax pair, then the eigenvalues of x will be the constant of motion of the given differential equation. So in this case, we are interested in this one and this final product. However, as we said previously, we can analyze them by using the different PDE on the Lie group, which, for example, have this nice property, and we can do. We have more freedom there, but we are more interested in the final product, and we can do it by using the previous theorem. And in general, we can go a little bit further, meaning if we have some general system that can be expressed using the fundamental vector fields of any Lie group action, we are going back to the beginning, meaning every such a system that can be introduced by using the Lie group action on some manifold, on arbitrary manifold M, and has this form, can be transferred to the PDE Lie system on the, in this case, in such a manner, on the PDE Lie system of the Lie group. So this was like third example of the PDE Lie, the first example from different parts of maths and physics that could be described as a PDE Lie systems. And to know what, okay, so we see that there are some examples. However, we want to describe them geometrically. And of course, the main usage, main structure to do so for now is using the K-contact geometry. So I recall some basics, the information about this. So by the basis of the K-contact geometry is a notion of K-contact form or K-contact distribution, but for now I will stick with the form one. This will be more useful for now. So the K-contact form on some open, this is the general definition that are operating on the open subset. However, later we'll drop it out, but in general, this is the open subset. And the K-contact form such as open subset is a differential one for on U, taking values on Rk, meaning if we want to write it, it will be just the sum of the tensor product of the basis of Rk. And we require three conditions, meaning the kernel of such a eta belongs to the tangent space, of course, of U. And this is the regular non-zero distribution of rank K. The kernel of d eta, it belongs to the tangent space of U. Once again, is a regular distribution of rank K. And the most important part is that those two kernels does not intersect, so the intersection is zero. And as I said, if there's no problems on whole manifold, if it's well defined on whole manifold, we call the pair M eta a co-oriented K-contact manifold. And the important notion associated with the K-contact form, K-contact geometry on itself is, of course, the existence of the rim vector fields. So if we have such a co-oriented K-contact manifold, there is a unique family of vector fields. Once again, this is the K vector fields, and because they are commuting, as later said, This can be expressed as a k vector field, called the Rib vector fields, or k Rib vector field that fulfills such equations. As we can see in the case, for example, k equals 1, we are receiving the traditional, the standard Rib vector field, meaning the contractions with eta is 1, or in this case delta if we are multidimensional, and it spans the kernel of the eta. And this is the existence of these Rib vector fields are pretty useful for us to impose some dynamics, or some Hamiltonian dynamics on our k-contact form, and to analyze it via such a dynamics.
Sorry, just a comment, Tomasz, because here you defined k form, yeah, k-contact form, but there are other definitions of k-contact form in the literature. Okay, they are even published in the web journals, and there are maybe even before to that introduced Narciso and Xavier. They are in reality more restricted than these. Okay, indeed, what they satisfy, for instance, is that not the differential of the eta has kernel rank, but every one of the coordinates of eta, not differential of eta, have kernel k, yeah? And it's pretty similar to this, and you will find, for example, Reb vector fields, you will define also Hamiltonian vector fields and things like that, but many of the things that are there, as they are a particular case of this, they can be retrieved quite easily. So for Xavi, for example, there is a fun thing, because there have been theories they have developed that there are quite probably particular cases of the things Xavi or Jordi or Narciso did. So maybe you should take a look, because they are published in very good journals. Maybe you should write a paper one day about how your theory describes all the ones that they were established before. This is just a general comment, okay?
Okay, I for sure will look at it. So, I mean, this definition is which we use later, so I will stick with it. But for sure, just for the clarification and comparison, I will take a look. Thank you. But once again, if by sticking with this definition and with vector fields, we can impose some dynamics by introducing the Hamiltonian vector fields, and there will be two different Hamiltonians. For example, eta Hamiltonian, just to emphasize that it depends on the chosen k-contact form. So if we have a k value, rk value function, a smooth function belonging to the infinity on a co-oriented k-contact manifold, we'll call it a k-Hamiltonian k function if the given concrete vector field with the concrete concrete vector field satisfying such a system of equations. So we have a k equations, two k equations. One is that each element of eta alpha contracted with x is giving us an element of this bold h, and the contraction with the eta is differential of this entrance of h alpha minus the sum, minus the Rib vector fields, each Rib vector field acting on a specific element, and times the element of eta. And the dispair h, we dispair h and x, we call respectively eta Hamiltonian k functions and eta Hamiltonian. Sorry, there should be k vector field. I don't know where is k. So it should be a vector. No, this is the precise that will be eta Hamiltonian vector field, not k vector field. So just to be precise, just to be, it will be useful to later to rewrite given equations such a more simple manner. Meaning, if we have we can rewrite it in such a manner that we can present a contractions with the bold eta, which is exactly what we write upper, but we understand it. However, the second part also is intuitive up to this point, meaning we can introduce new notations by this Gothic R, and the R eta is exactly what we can see. One can see if we contract and so on. If we do all this thing, we can retrieve the previous definition. However, this is more elegant one and will be in handy later for some proving. So this is the definition of eta Hamiltonian K function for the eta Hamiltonian vector field. I want to emphasize there should be vector field. I'm really sorry. However, we can do like the opposite, I would say, meaning we can have a one because this is the main difference. The bold H is an RK value function, so we have K components, and then only one vector field, which is eta Hamiltonian. What we can do by introducing the K vector field, a K vector field with only one regular function, which also will be called eta Hamiltonian function. In this case, the condition is similar. However, now we are summing over all contractions. So now if we have a K vector field, which is the family of K vector fields, and we contract it with each d eta alpha, in this case, there should exist one function H that fulfills these conditions and the second one. And this pair, once again, H not so bold H should be the eta Hamiltonian K function, and the normal H, the normal X should be vector field eta Hamiltonian, and by switching it, we have a bold X as a eta Hamiltonian K vector field and X as a eta Hamiltonian regular function. And this might be a little bit confusing. However, the notion is that because for the PDE listings, we are working with the time-dependent K vector fields. And previous works, what we are doing for the ODEs is we are looking at this vector field that's spanning the Sod-Goldberg algebra of these systems as a eta Hamiltonian vector fields regular. And following theorem, which I will give you, is that if we have a K eta Hamiltonian regular vector fields relative to a oriented eta contact manifold, then the eta Hamiltonian K vector field is, this vector field, K vector field, is exactly eta Hamiltonian K vector field. There are many terminology, but I want to emphasize that previously we are dealing with K separately vector fields, which were eta Hamiltonian, and now we are working with one K vector field, which occurs to be eta Hamiltonian as well. And as a proof, is just pure calculations, meaning we are taking each x1, x2, and so on, and xk. We are taking each eta Hamiltonian, should be eta contact eta Hamiltonian K functions. So this occurs. And just by contracting by the dual basis, because this can be expressed using the basis in RK, just by pairing them with the dual basis and summing over K, we can obtain the condition that I was talking about previously. And this is now we can see precisely what is the eta Hamiltonian regular function, eta Hamiltonian function, meaning this sum over pairing hi if with I. This is exactly our looking eta Hamiltonian function. So in other words, our pair x1 to x3 and so on to xk is an eta Hamiltonian K vector field. And this is important because we can analyze now, we can use the results that we obtain from all these for the eta Hamiltonian vector fields, then generally the analysis in the PDE Lie framework. And once again, I wouldn't be myself if I didn't give you some example later. So now we can define finally what is the K-contact PDE Lie system. This is the main part of this talk, meaning the K-contact PDE Lie system is triple consisting and manifold, eta meaning the K-contact form, and the time-dependent K vector field. This is exactly how it looks. With the smallest Lie algebra, meaning what we are talking previously, that each one of H can be expressed via some Hamiltonian, some vector fields that spans the finite dimensional algebra, and which one of them is eta Hamiltonian vector field. This is the main point by view of the previous theorem. And as an example of the K-contact PDE Lie system, meaning the PDE Lie system that can be described using K-contact framework, is once again related to Floquet theory, but I don't want to go to the details. This is the consider of PDE Lie system of such a form that we have an element of the general linear group of, so this is the invertible matrices 2 by 2, and the differential by, this element can be is parameterized by two elements Ts that are from R2. So as we could later see, it will be described by R2 dependent vector field. And it can be a little bit more, can be rewritten in a little bit more compact way using exactly the R2 dependent vector field. So this X1L that depends on T, S, and A is exactly just matrix A times some functions that depends on time and on parameter T and parameter S. And once again, because why we want to rewrite it in such a manner, because now we can easily see that indeed there is a associated, this is the PDE, the system is associated with RST dependent 2 vector field, exactly as written like that, with some additional condition of integrability. Yeah. So if it fulfills, this is the PDE system related to the ST or R2 dependent 2 vector field. And by using, and then now we want to use our theorem that previously said, meaning if we consider only this XL1 and XL2, we can, by once again, this is useful that GL will be a Lie group because we can find, because we can represent it as a left invariant or right invariant vector fields. And for free, we have a right invariant or left invariant 1 forms dual to the neutral element of GL2. And this is important because the natural construction, the most simple one to construct the, in this case, two contact forms, meaning by introducing the right invariant 1 forms that are dual to the basis that fulfills such a commutation relations, we can easily construct 2 contact form. In this case, will be eta R2 plus eta 4. And even now we can easily see that it is indeed a 2 contact form. And by just pure calculations, but verifying the previous formula, we can make those 2 vector fields into R2 dependent eta Hamiltonian vector fields, meaning we can check this, and we can check their eta Hamiltonian 2 functions, H1 and H2. And by using the previous theorem, we now know that our S2 dependent 2 vector field X is eta Hamiltonian 2 vector field with such a functions that we are just pairing H1, H2 with the dual basis of R2 in this case. And finally, summarizing everything, we have that our manifold, which is GL2, our contact form, which is eta, and our 2 SL or R2 dependent 2 vector field, which describes the domain and the image, is a 2 contact PDE Lie system. So we can explain, so we can construct easily in this framework, we can take the PDE Lie system and make them to the K contact or 2 contact, 3 contact, K contact PDE Lie systems. And this is important because now we can try, and this is the last example, but I will say about some future works with that, because PDE Lie systems, as occurs, there are a lot of examples from different parts of maths or physics, and they appear mainly, as we can see, we can describe them as a PDE Lie. Many systems can be described as a PDE Lie systems. There are some that I didn't mention, for example, some that are applying the hydrodynamics equations, for example, the Bäcklund transformations. So some transformations from one differential equations to another could be a PDE Lie system. Some conditional symmetries, meaning the symmetries related to some then some subsets of solutions to the partial differential equations. All of them can be derived as a PDE Lie system, and as a first step to analyze them further, so get something new, for example, the constant of motions, master symmetries, and so on, is via, for example, the K-contact geometry. This is our first approach. And of course, we can, there's some potential to generate, I believe, what is the most important part, meaning the superposition formulas for PDE Lie systems, because this is what characterizes the systems. And the future work would be, for example, trying to applying, because for ODE, we know there exists a coalgebra method to obtain the superposition formulas. For PDE, it's still to be discovered. So, for example, using the as I said previously, the eta Hamiltonian functions, two functions, or just the eta Hamiltonian function itself, it could be possible to generate it, and is the future work for now. And I believe this is all from my side today, and really thank you for your attention. This is the literature, and as I said, there are a lot of places that you can read a little bit more, mainly about the examples, meaning the background about the examples. I'm not an expert, but for example, the thing that describes the G structure will be this Dubrov-Komrakov. Phase splitting of periodic Lie systems is exactly the more explained about the Floquet theory, and so on and so on. So this is the main literature I use. And for now, this is from my side. And thank you really for your attention.
Thank you, Tomasz. So, is there any question? Comment, remark? Well, yes, a couple of comments. The work by Dubrov and Kombradov that talks about G structures links these PDE Lie systems with Cartan geometry and things like that. This is something that Timon Frelich suggested indeed to me. He showed me this paper, and together we found different things. And Timon suggested several ideas to make some application of Cartan geometry, but to K-contact geometry to this PDE Lie systems, but everything was left open. So now there is nothing in this direction. This is one thing. The second comment is about the coalgebra method for K-contact Lie systems and PDE Lie systems. And well, with Tomasz, we did a couple of things, but it turns out that it is quite difficult technically, and there are several issues that make the coalgebra method do not go as smoothly as in other cases. So this is something interesting to see in the future.
But also we say that it's possible with some additional assumptions.
Yeah, the thing is that you can add several assumptions as you know, because we did. But in any case, these assumptions, they seem to be something ad hoc. Well, at least this is my feeling. And probably there is some better approach to it, but in my case, I have no idea right now about how to do it. So that's all. Thank you. Any other comment? Okay, so thank you very much for your attention, and we will see you next week. We have a minute. We have a talk by Robert Volak from the Jagiellonian University. He is to give us still the title, but it is something about the Sacchian geometry, if I'm not mistaken. So thank you very much for your attention, and see you in a week. Thank you. Bye.